Hello and welcome to the BS Academy. So recently IIT Bombay has changed their syllabus a little bit to the each branches. So according to the new syllabus, we have made these charts in our best possible ways, and these charts basically give you an idea how to prepare your own charts, because ultimately you have to make your own charts of every subject, and after that you will get that confidence. So basically these charts will give you the ideas and perfect information after referring all the reference books. Now the next subject is strength of materials, in which we have prepared total 5 charts are there. Let's begin with the first one, in which we'll include the basics as well as the simple stress and strain, and after the plane stress conditions. Before that, if you are new to our academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box.
Now let's start with some introduction about the strength of materials. Basically, in the applied mechanics, it is the branch of science which deals with the study of forces and their efforts over the body. Here in the forces, external plus internal forces, and in the body it includes rigid plus deformable. So here applied mechanics divided into three parts. First one is the engineering mechanics, then the second one is strength of materials, and the third one is fluid mechanics. So strength of materials, it is the branch of applied mechanics which deals with the internal resisting force and the deformation due to the externally applied load. And the basics of the strength of materials is used while designing any machine component or structure. It is one part of the applied mechanics. The examples or all the concepts we will include is only about the externally applied load. Now there are some assumptions which are taken in strength of materials. First one is materials should be isotropic or homogeneous. Then second one is member or body should be prismatic. Then third one is materials should obey the Hooke's law. Then fourth one is externally applied load must be gradually applied load. Then number fifth, member or body should be in static equilibrium, and Saint Venant's principle is applicable. Then sixth one is analysis is done on the basis of ensuring stress and strain only. Here effect of true stress and strain are neglected. Then seventh one is effect of body forces are neglected. Analysis is done on the basis of surface forces only. And number 8 is effect of residual stresses are neglected. Then number 9, the body should be deformable and it should be continuous. Then deformations should be within the limits only. Here note that if the above listed assumptions are valid, then only the strength of material equations will give the exact value of the stress strain and the deformation. Here factor of safety is used while designing because to follow these all assumptions which are really hard in the real life. Let's start with the basics. Once again, these all are very basic concepts and formulas the whole subjects of, but it will be really helpful to understand the concepts of the strength of materials during all the subject. First one, the diagram of homogeneous body and the isotropic body. The homogeneous body is independent with respect to the location, and the isotropic body is independent with respect to the direction. And third one is the anisotropic body. It neither homogeneous nor isotropic. Then fourth one is orthotropic body. In the orthotropic body, properties are different in all three perpendicular or all three orthogonal directions. And fifth one is prismatic body. For that, same cross section throughout the whole body. Here, three types of load. First one is static, then fatigue, and third one is impact. Then after engineering stress is equal to P by A and true stress is equal to P by AI, where in the engineering stress you have to take the original area, and in the true strain you have to take the area after deformation.
As you can see here, first one is the load. It is any external force or couple to which a member is subjected during its functionality. And there are two types of load. First one is normal load, second one is shear load. Normal load is always perpendicular to the cross-sectional area and shear load is parallel to the cross-sectional area. Then after one diagram for the axial tensile load, then after eccentric axial compression load and eccentric axial tensile load. So S for transverse shear load and T for eccentric transverse shear load. Then after couples, here two types of couples are there. First one is bending moment couple, which is about the transverse direction, and turning moment couple is about the longitudinal axis. Then there are some examples are there. First one is for finding the turning couple at A, then second one is for finding the turning couple at X section, then third one is for finding the bending couples. Then after shifting load is there. If you want to shift the load from one point to another point, then you have to add one couple for that load, and here by applying two axial eccentric load it can produce pure bending couple. Then after classification of stress, first one is the normal stress and the second one is shear stress. Normal stress, it include two types. First one is direct normal stress and the second one is indirect normal stress or bending stress. And the equation for the stress you can use here, m by INA is equal to sigma by y is equal to E by R. And the second equation for shear stress, tau is equal to V A y bar upon INA into V, and T by J is equal to tau by R is equal to G theta by L. Then after coming towards the strain, here normal strain, then after shear strain. Normal strain is axial or linear strain, you can say that. Here epsilon x is equal to delta L by Lg. Similarly, epsilon y is equal to delta h by h and epsilon z is equal to delta b by b. Here L for length, h for height and b for width. And after shear stress, it is the change in angle between any two planes which were originally at right angles, and phi is equal to theta 1 plus theta 2. Then third one is volumetric strain. Epsilon v is equal to change in volume by original volume. Epsilon v is equal to epsilon x plus epsilon y plus epsilon z. There are 9 terms for the stress in the direction of x, y and z. Then E is equal to 2g into 1 plus mu, and E is equal to 3k into 1 minus 2 mu, and E greater than k greater than g. This note is very useful in the examination. In every year there may be questions for the equation of E, G and mu. Then here for the material of homogeneous and isotropic, the minimum number of elastic constraints required are 2. Then for orthotropic 9 constants are required, and for the anisotropic 21 constants are required. Then after Poisson's ratio, mu is equal to lateral strain by longitudinal strain, and mu is equal to minus epsilon y by epsilon x, and epsilon y is equal to epsilon z. Then minus 1 less than or equal to mu less than or equal to 0.5. And there are some values of mu for general material. Mu is equal to 0 for coke, then mu is equal to 0.1 to 0.2 for concrete, then mu is equal to 0.3 for steel, then 0.25 to 0.33 for engineering materials, then 0.49 which is near equal to 0.5 which is for rubber. This value of mu is important for the rubber. Then mu is 0.5 for all incompressible materials. Then for general, mu is equal to 0.33 and k is equal to E. Then after 2D plane stress system, for that the equation is there. Then examples are beams and shaft. And for 1D loading, sigma is equal to sigma xx 1 cross 1. Examples are like bar, rod and column. Then strain system is there. The equation for epsilon you can see there. And then there is one table for stress strain system and total number of sigma or epsilon component needed and independent number of epsilon component required. Here for 3D, 9 components are needed and from that 6 are independent. For 2D, 4 components are needed and from there 3 are independent. And for 1D, 1 component is needed and that is independent component. And then after elastic constant, first one is Young's modulus. E is equal to sigma by epsilon, which is equal to stress by strain. And here note that sigma is equal to constant for material, and if E will increase then epsilon will decrease. Then shear modulus G is equal to tau by phi. Then shear modulus is also known as the modulus of rigidity. Then third one is bulk modulus. It is only designed for the hydrostatic pressure condition, where sigma x is equal to sigma y is equal to sigma z is equal to p. K is equal to p by epsilon v. So you can say that K is equal to p by del v by v. From there delta v is equal to pv by k. These equations you can use in the MCQs. Then after longitudinal strain, it is normal strain in the direction of load, and lateral strain, which is transverse strain, it is the normal strain in a direction which is perpendicular to the direction of load. Every longitudinal strain is associated with two lateral strain, and nature of longitudinal and lateral are opposite to each other. So this is all about the basics of the strength of materials. So from the basics, the equation of normal stress and shear stress is very useful in the SOM as well as the MDID, and the equations of E, kg and mu in the terms of each other is also very useful. Now in the second chart we'll include 3 chapters are there. From the first one we'll keep some basics also there. Now in the second chart we'll include the 3 chapters are there. First one in which we'll include some more basics like Hooke's law, then thermal stress, then after axial deformation. Then in the second chapter centroid and moment of inertia, and the third chapter will be SFD and BMD. So if you like this video, please do like and subscribe to the BS Academy and press the bell icon for the upcoming charts of strength of material.